today we're going to talk about dimensions and tolerances. We've already kind of talked about them a little bit, right? But we're going to go in more depth today on all the different details of those things. So the drawing, the picture tells us what about the part?
How big?
Does it tell you how big?
What it looks like.
Just the picture, the lines. What does that tell you about the part? It does?
What it looks like?
What it looks like, right? It tells you the shape. The picture shows you what shape it is, right? The dimensions tell you how big it is. They tell you the size. And it tells us mainly how to inspect the part. So you'd think that it would tell you how to make the part. It kind of does. The dimensions that are there are the ones they want you to check. Make sure it's made right. Okay? So that means sometimes it's the ones that help you out to kind of figure out how deep you need to cut or whatever. Sometimes not. They're kind of depending on what the use is. The dimensions are there for the inspector. The person's going to check it to make sure it was made right. Questions on that? Kind of important point. All right. So in dimensions, we have several different types of lines. So we have angle lines. So here, pointing at this hole, that's called a leader. Okay, just an arrow pointing at it comes up and then has the dimension, just like we talked about with specific notes, right? Remember when we do that same thing and call it out knurl or whatever, the leader. And then within a regular dimension, we have two different types. We have extension lines here. They go from the part out. And the two extension lines, in most cases, are going to be parallel. Okay, so the extension lines come out, and then between the extension lines, we have the dimension line. So that has the number in it. That tells you what the measurement is from the end of that arrow to the end of that arrow. Okay, which is the same as this from there to there. Okay, make sense? So what kind of a line is this? Extension, right? It's coming from the part out to where the dimension is. What kind of line is that? It's dimension. Got arrowheads on it from one extension line, and in this case over to the part, to the dimensions in the middle of it. Leaders are always straight lines coming out, usually from holes and things like that. Okay? Questions? So when you're looking at a part, we have the dimensions, and some of the dimensions tell us the size of things, some tell us the locations of things. So, like the green dimensions are all location dimensions. They're telling us where things are. And we have red dimensions that are telling us the size of things. Like right here, this dimension here, this 1/4 inch, that's kind of both the size and location, right? It's telling us a size of how much is left there, but also it's telling us the location of where that slot is, where that groove is, right? So dimensions can be both size and location. But for everything, so like holes, we need a size dimension and location dimensions. So when you get a set of drawings, you need to look at it. Okay, do I have the size of everything on here? Do I have the location of everything on here? Okay. You will get drawings that don't have all the dimensions. It happens. It's your job to make sure that it's got everything you need to make it. Okay? What happens if you find it and there's no dimension? This dimension's gone. Tells you how far down that hole is, but doesn't tell you how far over.
Called it.
Column. Don't guess. Pick up the phone, go talk to your boss, whatever. Get someone to contact them and then tell you what that dimension is. Usually they'll make a change, send you a new drawing with that dimension on it. Okay? Questions? Sometimes people don't know what that they're doing. This is an actual drawing I found on Facebook that someone posted to a group saying, what is this? What does this mean? Like, how am I supposed to make this? The person didn't know what they were doing that drew this. Did I show this the first day?
Something like that.
Oh, and I showed you how it is, how it should have been,
Yeah.
with correct dimensions and everything. So just that is, get the crappy drawing. Might have to figure it out, or you might be able to say like, hey, I can't understand this at all. Like, you clean this up a little bit and send it back. Okay. So most of the time, we dimension individual parts. So we do drawings of one part at a time, and then those part drawings get the dimensions of how to make that individual part. So that's all of the drawings we've been looking at so far for the quizzes are like that. They have assembly drawings telling you how to put stuff together, and then part or details with pieces of how to make each piece, right? Sometimes you'll encounter, guys, class started 10 minutes ago. Sometimes you'll encounter things where all the dimensions are on the assembly. Class started 10 minutes ago, 12 minutes ago. So this is not the best way to do it, but some people do it, especially on like weldments. We got a bunch of just tubing that's got different lengths, different angles. They might just put that all in one drawing and kind of call out all the dimensions and angles and everything all at once. It works. Not the way I like to do it, but it's an okay way if you can figure it out. So you might encounter this one, got a lot going on. Woodworkers like to do this stuff sometimes. Like I went to old woodworking magazines, and they're all like this. Just the whole assembly with all the dimensions on it. Like, good luck trying to make this. You will see these sometimes. So then you have to figure out what. If you got this drawing, what do you have to figure out?
Everything.
Everything. So you need to figure out how many pieces there are, right? Then each dimension for each piece. So if you got something like this, let's pretend this is a metal table. So no way it fits for you guys. Let's pretend this is a metal table. You get this drawing. What should you do?
Find out how many pieces of metal you first.
So how are you gonna do that?
Start counting.
Yeah. Because I'm seeing 1, 2, 3, 4, 5, 6.
So probably get out a piece of paper, start making a list of all the parts you can count up, right?
Yeah.
And then kind of figuring out, and then what? Oh, that's got to be inches.
That's a big ass table.
If that's 38 feet, that's huge.
38 foot piano bench.
So I'm guessing these are inches. But what else? What after that? So after you figure out what the parts are, or even after as you're starting to figure out what the parts are, what should you do?
The material is you're using.
Well, yeah, of course, you need to figure that out. You're missing a step.
Do you need to cut it or?
So let's say you call them and they're like, no, I'm not sending you a new drawing. This is all I'm giving you. I want these. What should you do?
All your buddy.
What's the other half of this class?
Sketches.
I'd probably sketch out each part, right? So that way you can now you can make your own drawings of each part. So you know what each part needs to be. Okay? So that's another reason why we have the sketching piece. Sometimes you have to sketch to kind of take what they give you and figure out, okay, if I'm going to make this, I need these things. Okay? And whether it's for you or it's, let's say if it was a welded frame or something. Got all these minor cuts there. And they give you dimensions. And they tell you that that's 2 by 2 by 2 by 2 by an eighth square tube. So that's what they tell you. They give you this drawing. You have enough information to make this, right? But now what do you have to go and you have to figure out, like, nothing tells you how long that piece of metal is, right? It tells you everything you need to know to find it, but you can't just say, all right, I've got this now, I can cut all my stuff. And so probably there's one guy, maybe one of you guys working the bandsaw. You tell them how big to cut stuff, right? So you're gonna have to figure out what this is and whether you're gonna do a sketch of it or try and write it down somehow and have them get the cuts at the right angles, all that stuff. So probably do a sketch of it, you know. Put those dimensions on it. So they know, okay, these two are the same angle. There, at least now he knows what to cut, right? So there's still part of that you get a drawing that's just the assembly. You're gonna have to figure out and probably make your own drawings of the parts. Okay. So that's part of why we have the sketching in this class. Questions? Yep.
Is it harder than the original assemblies? How they make that?
What do you mean? Is it hard to do?
Is it harder to do it like that, or just you saying like
It's
like that, or?
It's because they're too lazy to make all the different drawings themselves. If I was going to do this, I'd actually make the drawings of these parts. If I'd make that one.
How would you even do that?
I'd make that one. This one and this one and this one are all the same, and that one, and that. So make like this one. These four are basically the same, right? They're all this shape. Yeah. And these two are both that shape, right?
Oh, no.
They're just different sizes, right? So I'm going to come back to this after we get done, okay? But I would do drawings showing this stuff. And so I did a project like this. There was an almond tree shaker where the whole thing was square tube or rectangle tube. And a bunch of cuts like this at different angles. Some at 45 to make 90-degree cuts. Some at 22 and a half to make 45-degree cuts. Some at other angles. What? Some with one angle this way, one angle that way. Yeah, so lots of different cuts. And we actually made drawings to tell them how to cut each piece. We didn't just give them the assembly and say, hey, figure it out. So I'll get back to this in a minute. So just beware, you will get these. So it might take you some work on your side to figure out what you need to make in order to make that final product. Hopefully it comes into the shop. Someone in the office is going to do that for you. So when I worked at Harris, that was my job. If they brought in a drawing that had like an assembly, they had all the stuff, I figured out all the pieces and then did new drawings for the shop. So that way the guys in the shop didn't have to figure it all out. We have some dimensions that are called reference dimensions. So here, there are these ones with parentheses around them. So kind of show you kind of how wide that opening is, how tall it is, and how wide the whole thing is, including the screws and how long it is. Okay? So parentheses around it, can't talk today. Parentheses around it means it's a reference dimension. That means the inspector is not going to check it. We've already made this piece. We've already checked this end piece to make sure that that piece is right. You put these screws in, he's not going to go back and recheck that width and say, oh, no, it's too wide now. Just because that's just the size of the screw. That doesn't matter, right? The overall length, if all the parts are made right, that's what it's going to be. We don't need to go inspect it again. But things like this, where this screw needs to be backed out that much, that is something that is going to be inspected. We're going to Loctite that screw, put it in, back it out that much, so that way it leaves a little play. But that's going to get inspected. Make sure that it's right. Okay? Questions? So what does parentheses mean?
Overall length.
No, this one is an overall, but what does the parentheses mean? Reference, which means what?
Doesn't have. Not going to be checked.
Don't check it. It's just there for information. When we have multiple parts that go together, they're going to be dimensioned the same way. So here I have 3 pieces that are from that vise, and if I look at them, this dimension is the same as that dimension, same as that dimension, right? Where the slot is, here and here are the same, right? They're both dimensioned from the top down. They look pretty similar the way they're done. Okay? You should see that on a set of drawings. If you see it on the set of drawings where this one's going from the top and this one's going from the bottom, then there's might be something going on. Okay? But seeing a drawing like this, now you can see, okay, that and that and that are all the same. That's going to line up. Okay. The person doing the drawing, if they do it this way, makes it easier for you guys to understand. But also, the tolerances, what we'll talk about next, all kind of go the same way. Questions? All right. So there's three different types of dimensions. One is called baseline. So we're starting from one line, and we're just measuring from that line up to different things. Okay? That's called baseline. We have ordinate dimension, which is the same kind of thing. We're measuring from here to here, from here to here, from here to there, like that. But now we're not going out away from the part each time. So I usually use ordinate dimension on things like this, where I'm having a lot of things like that, and on sheet metal for the bin lines. If you guys are going to work somewhere that has a sheet metal shop, you might see that. I use these dimensions other places on the drawing, but for the bin lines, I'll use ordinate dimension. It doesn't take up that much space. So I can easily, on something, have 15 bin lines. I've got hems and different things. I can get a lot of bin lines. That'd make this go like way out here. Half my drawing would be the space for dimensions. With ordinate, it doesn't take up that much space. Okay. And then we have chain dimensions. So we go from the edge to one thing, then from that thing to the next thing. Okay. Why do you think we might use chain dimension versus baseline?
That one that has more parts and pieces inside.
I could do it from here to there, from here to here, right? Why don't I just do that? And why do I go straight between those two things?
Because it curves.
Doesn't the center two domains?
What about those two things?
Equally apart.
No. And then here I measure from here to
where
here.
the pen starts and ends.
measure extra
What's different? What's different between these two things versus these things over here? Come on, you guys are thinking too much. What's the obvious thing about those? What's a dot? A hole, right? So these two holes are related to each other. There's going to be one thing that goes through both those holes. Another thing is going to go through these holes, right? And so if things are related to each other, I'm going to dimension them from each other. So on the other part, those holes are dimensioned from one hole to the next hole. We'll do the same thing here. So if you see a chain dimension, it means that those things are in a pattern of some kind. It's important that that distance stays the same. Like over here. Oh. But if we look at this part, this hole right here is on a radius dimension. And if I look at the part that goes right there on top of it, that goes through that hole, and it goes over here, that little clip, it's got that same radius called out. Or it's a chain dimension, but it's that same number. Let's see. So here's that. The radius of that circle is 688. If I go and look at this piece, 0.688. It's not a measurement that's going straight across or up or down. It's going from that center point to that center point.
So is it just holes? Can it be square?
Yeah. So yeah, if you have a dimension that goes between two things, it's not just coming from the edge over. It means that those two things have to be related to each other that same way. See, also here, I have, what's this kind of dimensioning called? What was that? What's that? Ordinate. So I have ordinate dimensions here because the edge of the part, a bend line, the other edge of the part. I said I like to use them for bends. Okay. And what kind of dimensioning is this? Baseline. So I measure from the right side over, right side over. Okay. And then we have tabular drawings. So tabular drawings are good so that way if you have similar looking things that are different sizes, we can have one drawing instead of a bunch of different drawings. Like on this piece from that U-joint, you can have different size U-joints that all use a part that looks exactly the same. Just the sizes are different. The diameters are different, the lengths might be a little different. But it's still basically the same part, right? Where else could we use something like this? What else? Yeah, so bolts, screws. So anytime you look at that catalog, you're looking at a tabular drawing, basically, right? You've got a little drawing at the top with some letters on it, and then the table on the catalog has a column with a letter on it and a bunch of different sizes, right? The tabular part. Things are all kind of the same but different sizes. What else have we talked about tonight or today that we could use this on? What have I talked about during this lecture that we could use this on? Hello? You guys are awake? Have you been sleeping through this whole thing? not Friday, it's Thursday.
It's our Friday.
Mine too, but if you're not getting this, the next hour is going to be really hard. And you have to get this because there's 2 quizzes today. Or that you have to do over the weekend. 1 quiz for this stuff, 1 quiz for the next stuff. Oh, it is, huh?
Yes.
Then you better do it before Sunday. All right. No? No one can think of where else this could be used? Something that I did earlier that I said we'll get back to later. You forgot. You know something, but you forgot it, right? What? What were we talking about earlier?
The frame.
The frame, right? This frame, right? So let's say, let me put some actual numbers on this thing. Okay. Call this 10. Oh. Call that 15. Call that 30. Call that 20. And we'll call that 10. Okay? Now we've got some actual sizes for this thing, right? And so and then I'm going to label these parts. We've got A, B, C, D, E, and F. Okay? A, B, C, and D are all basically the same, right? Just different sizes. E and F are basically the same, different sizes, right? Yes? You guys agree? So maybe up here, I call this, I do a drawing for this piece, and so I can call that dimension A. I tell it this is 2 inches. That's 45 degrees. Okay? There's my drawing for that part. What's the parentheses mean? It's reference, just for information, right? I'm using 2-inch tube. I don't want them to measure that tube and be like, oh, it doesn't match the tolerance on how to block. We need to shave off the outside of it a little bit. Make it 2 inches. I'm using a 2-inch tube. It's got some tolerance there. It's okay. It's going to work. Okay, so I put it in parentheses. I don't want it to inspect that and be like, no, you need to sand that down a little bit. Right? So I do that, and then I make a table. So E, F, dimension A. So now I figure out E is, that's 15, minus 2, 13. That means that's 17 from there to there. Oh, but it'd be 15, right? Because I'm measuring from there to there. That's just 15. That's 15. That E dimension, right? This one, I think from here, measuring this line, 20 minus 10, so that's 10. And now I have this drawing right here on 1 sheet of paper. Tells me everything I need to make. I know everything I need to know to make 2 different parts. The tabular drawing. And I have this one, do the same thing. How many parts? This is 4. kind of squeezed in here. So A, 30, B, 15, C, 20, D, 10. So now I have this sheet of paper with that other piece of tubing on it that covers 4 parts. So now instead of having 6 different drawings, whereas I've got 2 drawings, right? Now it's easy to send it over to the guy running the bandsaw and say, okay, I need 1 of each of these sizes. I need 2 of these at those sizes, right? Makes it a lot easier to understand. So that tree shaker that I was talking about, I basically had this, except I combined both these onto one drawing. And so I give it like the overall and then give it here. I made it a little bit different. Probably had 40 something parts on one drawing.
Like 2.
All different sizes.
Got 2 of each, or
yeah. No, 40 different sizes on one. Because the angles weren't all 45. And so I had it, we had to adjust that on one sheet of paper.
isn't that a little busy?
Nope, because it was a simple drawing. The way I actually did it was but this was actually a little shorter. But I give it so this was A, this was B, this was C, that was negative C. So C was positive, and I did a kind of a break between the two. So if on the table, if C was positive, then the part looked like this. If C was negative, the part looked like that. So I had one drawing, I can control all these different ones. So if C was 0, what does that mean? Then it's straight up and down. So with this, I could control parts that look like this, parts that look like this, parts that looked like that, parts that look like that, and parts that look like that, right? These are actually the same thing, right? Whatever. So I got 4 different shapes of parts I can control without one drawing. Okay? And if that's a part, if one of the tubings had, if it had a hole in it, then it got its own drawing. If it was more than just the length cut at different angles, then it got its own drawing. But other than that, one drawing, tons of parts. It made it a lot easier because now they had one thing to look at. We don't cut this part, they just go down, find it, look at the measurements, they got it. So I had to thumb through 40 sheets of paper, right? We're having to look at this view of a lot more things and figure it out themselves. Okay? So that's a tabular drawing. It helps out a lot when you're doing stuff like that. Any questions? Yes, no? No? All right. Oh, we've got a few more. I thought that was the last page.
So tabular drawing is kind of like mechanical drawing.
But these are all mechanical drawings. Yeah, everything we're doing so far is all mechanical. So, but it's anyway, a lot of different things, the same basic shape. So if we have a cylinder, you're gonna see the dimensions out like this, where you can see kind of the side view of the cylinder, not where you see it round. Usually for holes, we see the holes where they're round, and that's where the dimension goes. For cylinders, you'll usually see it where you're seeing the side of it. Like if this was it, I just tell you a diameter here and then the length, right? This view doesn't tell you anything else. You can't get from that.
No, you're not seeing the length.
Yeah. So here you get the length and the diameter. Here all you get is the diameter. So kind of the standard is cylinders, like the outside of the cylinders, are dimensioned where you can see it from the side, not where it's round. Holes are usually dimensioned where they're round, but if there's something complicated going on like this, now we can look at it and dimension them here also. They will have the diameter symbol. So now by seeing that symbol, you know that it's round, right? What's this kind of a view called? What kind of section? No. Full section. Because a full view is a section, right? Half section, only part of it, only half of it would be a section. A full section. Any questions on anything you see on this drawing? It used to be here. I don't know where it went. I think it disappeared. It's a tow rope knob from Malibu Boats. So you know they've got the pole that sticks up. It's got the little knob on top. The rope goes for point skiers. That's the rope goes around right here.
So this one's always going to be round?
Yep. It's diameters, 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 diameters. All the numbers going this way on the page are diameters. So you know it's got to be, everything is round. Okay. Any other questions? And that was the last drawing. All right. So let's take a break. All right, take it back over. No. Too bad. All right, so now we're going to get into the tolerancy. So I kind of missed a section though. So right here on Canvas, there's this. What does ASME stand for?
Some mechanical engineers. American Society of Mechanical Engineers.
American Society of Mechanical Engineers. So it's an ASME standard. The standard is Y14.5. And the year that was adopted was 2009. Okay? This is the standard that covers dimensioning and tolerancing. So it's there if you want to download it and look at it. It's also on the computer. So you go to the computer and go to that V40-4 drive, and then go to reference. It's right there. Now you don't have to spend time downloading it. It is 227 pages long, and that includes kind of the forward and stuff. Everything we talked about so far is here. So dimensioning angles and things. We didn't talk a whole lot about it, but when we're talking about key seats, this is how they should be dimensioned on the drawings.
Kind of like a reference point.
And I look at the pictures. Everything important is in the picture. So like if you're having to do a drawing and you're not sure what to do, look at the pictures. and then just copy what's on the picture. If you want to know why or some more information, then read the paragraph. But I went through these when I started here and bought all these, and I learned a lot of stuff that I was taught wrong back when I went to school. So everything we talked about so far is up to page 23. So 35 pages into this document out of 227 is everything we talked about in the last hour. Now we're going to talk about, so that was all section 1. Now we're going to talk about section 2, general tolerancing. And that only goes another actually, we're already past it. That only goes like another 4 pages. So it just goes to like here, to page 27. So the next hour, we're going to talk about stuff that covers 27, or covers 4 pages in the standard. And so that's still a total, we're still only on a total of page 39 of this whole document. So all the rest of it is what's called GD&T. And that's what we'll talk about on Monday. We are not going to go through every nook and cranny and detail in it. Okay? We're going to go over the basics of GD&T on Monday. But so today we're going to go over general tolerancing, or right now we're going to go over general tolerancing. And that'll take us, through the first 30 pages or so of the standard. And then we'll cover a little bit of stuff that kind of covers, and it'll cover the basics of the rest of the book. But GD&T is one of those things that if you learn it, you can get paid a lot of money just for knowing it. I got a job once where I said GD&T, they stopped the interview right there, and made me an offer. Just because I knew that it was an important thing, and I said the things. Of course, I had to show that I actually knew what I was talking about. What is it, GD&T? Yeah, we'll talk about it Monday, so don't worry about it right now. And after getting this and actually reading through this, I realized that I didn't know shit. Because I had a full semester class on GD&T. But all it was how to read the symbols and put them on the drawing. I had no idea what they actually meant. Just like if it said the prompt said put this tolerance here, I could do that. But I didn't know what it meant or how it was used or any of that. So when I started here, I started teaching this stuff. It was like I should probably figure it out. So I got all the standards, read it, and like, oh, yeah, I didn't learn any of that. Because when I did it, the teacher would put on a video, put on a cassette tape of some old guy sitting behind a desk, blah, 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 blah. I'd listen to that for an hour and a half. And then we'd get some stuff to do. You guys are going to know more after this class than I did after a full semester of that. Or not today, but after Monday's class, you'll know more than I knew after a full semester of that. All right, so now we're going to get into the general tolerances. So these are mostly size tolerances. Okay, so what is a tolerance?
How big you can make, big or small you can make.
Yeah, how much wrong it could be, right? Because things are not made perfect. They're not made exactly to the numbers shown on the drawing, right? Sometimes they are, but not all the time. And if we had to make them perfect every single time, we'd have a lot of scrap. So there has to be some allowance for what's good. So you have to have a range of sizes that's a good size, okay? So that's what the tolerances do. So remember we talked about tile blocks? We have the standard notes area, and it has up here the block tolerances. So unless we call out a specific tolerance somewhere, these block tolerances apply to everything, right? We already talked about that a couple weeks ago. So like this dimension 0.75, what's the tolerance on that?
0.02.
0.02. That's 2 decimal places. That's tolerance. What's the tolerance on this one?
0.1. 100%.
3 decimal places. Look, 3 decimal places. go to 3 decimal places,
Oh, that's
5 thousandths. Okay. So if we look at this one, 0.75, so that's the dimension with the tolerance. So that means that this measurement could be 0.73 to 0.77. If they make this, you measure it, and it's anywhere in between there, it's good.
Yeah, plus or minus. There you go, yeah.
Yep, so it's plus that and minus that. This one,
So if it's 2 decimal places, it's 1,000. Or 3 decimal places, it's 1,000.
now it can be between 1.620 and 1.63. Okay? So that's what the tolerance is doing. So the number of decimal places tells you it's important or not and how important it is, right? So most of the dimensions you'll see will be like that. Here's a look at it, how many decimal places is it? Let me look at the block, see what the tolerance is. All right, now I know my room. Okay? In case there's ones that we want tighter tolerances than this, then we have to call it out. Okay? Or the person designing will call it out. So if you see just a number, look at the title block, use that tolerance. We have what's called explicit tolerances, and these are where they're called out on the part. So here's my block tolerances for this page. What's the tolerance on that one?
It's nothing.
Really?
Oh, wow.
My block tolerance, right?
That's 4 decimal places.
So I'm just gonna nine. Right, that's the maximum size that could be.
On a
It was
regular.
plus 5 minus 5 10,000ths, right? It's 4 decimal places. I'll get the 4 decimal place one. It's that. So I just added 5 10,000ths, subtracted 5 10,000ths. What's the tolerance on that one?
2,000.
It's plus or minus 2 thousandths, right? So that means the size could be 002.998. And then the rest of these, they have tolerances called out. So it means that these don't apply. Because now we're looking at the tolerance on each one. Okay?
And that's what it means when it's otherwise specified.
Yeah, because now it's being specified. So yes, these are the tolerances unless otherwise specified. Now it's being specified, so now this was what applies. What do you see here? One of these is not like the others.
Oh, the bottom one only has 1. You can only go small.
No, but
Oh, wait, the second one, you can only go
See,
small. You
90.99.
can't make it bigger.
998. It's going.
most of these have something in common. One of them does not have that thing in common.
I'm seeing 0.6 on the bottom. That's 6 sizes. So it's 0.5.
What's that bottom left one? The 1,000 less.
Only go bigger.
Bottom right.
Who thinks this bottom right one is very different than the rest? And is the most different than the rest?
No, I say the next one that we're gonna do.
This one?
No, the other one.
Yeah.
This one?
No, other
No,
one.
This one?
yes.
What's different about that?
Doesn't have a set number.
So yeah, it's a different way of showing it. So if I made these holes, would all these holes be the same?
No.
Would they all,
You should.
would the same sizes be okay in all these holes?
No.
Or which ones would be different?
The ones that have the specific numbers on the side.
what if I tell you that most of these, the holes are going to be the exact same size? You believe me?
No.
I think I'm lying to you.
Probably.
Only one of these is different.
The 98, because that was way off. All the other ones are between 4 and 2. So in one way or another, they could all match up.
Nope.
Oh, one. We all have exactly one.
If it was a snake, it would have bit you by now.
Oh,
Right in front of you.
Oh, yeah, they're all one.
One of these is different. Just look at those first three. Just looking at those first three, you can tell one of them is different. What? Nope.
The third one.
So look at these three. The top one is different, right? These two are both from 1002 to 998, right? If you do the math on all these other ones, they're all exactly the same. So what's 1 plus 2 thousandths? 1.02. What's 1 minus 2 thousandths? That. What's 1.02? Oh, look, that's the same number that's right there. Minus 4 thousandths. What's that? 998. What's 1 plus 1? 2 thousandths. What's 1 minus 3 thousandths? 998. What's 999 minus 1? 998 plus 3? 02. Okay, now do you believe me? They're all basically the same. This one is different because its numbers are 005 and 99995. Okay, that decimal place makes a difference.
Yeah, but you still make it the same size. You still
Yes,
make them all the same size.
No, because if I make this one 998,
No, I mean, you can make them all like one, exactly.
if I made this hole, if this dimension was called out like this, and I made that hole 998, it fails. If I make this one 998, passes.
I'm saying you make them all exactly one, and you're fine.
If you make them exactly one.
That's it. You make them all-
But things are not made exact. Use a 1-inch drill bit, it's not going to cut a hole 1 inch diameter. Guaranteed. And it's not going to be round. Use a drill bit, the holes are not round. They're like 3 lobed. So this one is different. This more precise than the rest. But all these rest, the upper and lower limits of the tolerance are exactly the same. The maximum size of the hole and the minimum size of the hole is the same of what's allowed. Okay? That is true. Okay? Just accept it. But I just showed you, right? All of these, the upper number is 1002, the bottom number, small size is 998. But this leaves us with 7 different ways that this is shown. And actually 6 because these two are exactly the same, right? So that's both 1 plus or minus 002 plus or minus 0.02. So those two are both the same. Just one, I have to leave the block to get it. One is right there on it. Okay? But all the rest of them, that's 6 other ways, 6 ways to show the same thing, basically.
So that's what that
So
means.
what? So the next question is, why do we have 6 different ways to show that same thing?
Yeah, why? If you can.
Like, yeah. So why do you think I have 6 ways I can write this?
There's 6 different ones you can go.
No, because I can put this all in the same hole.
I mean, like size.
But all those mean the same thing. All these ones, all 6 of these I can make the hole 0.998 and it passes. I make it 0.997, it fails. I make it 1.002, it passes. 1.003, it fails. On all of these. The same hole, the same size will pass and fail all of these. So in how it's used and interpreted by the inspector, it's exactly the same. But why do you think I have 6 different ways to show it? I think you're thinking too hard again. Why would I show you different things? Why would I say it a different way in different cases? Preference. That's exactly it. But it's not personal preference, it's preference for the part. What do I want the part to be? So this one and this one, these are called bilateral. So this one, it's not there, but it's no, this is a bilateral tolerance. Right here, it's bilateral. Bi means 2, right? The 2 directions the same. So these, I want it to be in the middle. I want it to be the number I give you, and it can be a little bit bigger or a little bit smaller. Either one's okay, but I want it the 1 inch. Okay? So bilateral means 2 sides that are the same number. Okay? This one right here is called a limits tolerance. I'm just giving you the limits. I'm saying, here's the minimum maximum sizes of this, make it. As long as it's somewhere in there, I don't care how big it is. Okay? So I have, in this one, limits, I have no preference for the size. In bilateral, I want it to be in the middle. All of these over here are unilateral. Uni means 1, right? So 1 direction is the same. So both directions are different. So now I'm telling you what size I want it. So over here, I want it made big. But if it's smaller, it's okay. Here I want it made a little bit bigger than the middle. If it gets a little bit bigger than that, it's okay. If it gets smaller, it's okay. Down here, I want it made small, but if it gets a little bit bigger, it's okay. All right? So by the person that did the drawing putting a different type of tolerance, that tells you what they want. So that number at the front, that's what they would really want. That's what they would prefer. But the tolerance tells you what they'll accept. Okay? Does it make sense? Yes, no? Kind of, yeah. Yeah, all of these, this one, and that one are all bilateral. Unilateral. So all of these over here are unilateral. Bi means 2 sides, so 2 sides are the same. Unilateral, 1 side is the same. Lateral means side, right? You lateral the ball, you're throwing it sideways. You're not throwing it forward, back, you're throwing it to the side. So you need 1 side. By 2 sides. Any other questions on this? You do need to know what those words are. They are going to be on the quiz and probably the final. Bilateral for this. Unilateral for this. Limits for here. Okay? You do need to know what those are. Yeah. Yeah, so these are uni. These are bi. And that's limits. What? Yep. But lateral at the end. I'm not writing it because I don't know how to spell it. You should probably figure out how to spell it before you take the quiz. I'll show you some things that have it spelled on. I don't know the next one for tolerances. That's under those dimensioning 8 tolerances. Okay, so these are explicit tolerances that are called out for a specific dimension. Oh, here we go. Ta-da, a page with the spelling for everything. And so this is on the slides when you click on it in Canvas, so you can see the correct spelling. Okay, the limits, just give top and bottom. Bilateral, the same tolerance both directions. Unilateral, different tolerances each direction. We also have what's called a single limit. So like on a casting or injection molded part, when they make the mold, they have to put some radiuses in there. So like if they're gonna do a cast part, metal doesn't like to flow around sharp corners. It likes to flow around rounded corners. And so when they make the mold, they're gonna add some radiuses to it. And so on that drawing, the person might say radius this max. So casting radii 0.06 max. So it tells the people making the mold, you add whatever radiuses you need, but they can't be bigger than a 1/16 of an inch. Okay? And if the casting company says, no, I need to make this one bigger, then they need to call them and check it out. But anything they put in smaller than a 1/16 inch is good. When I was doing sheet metal, running the laser, so it's anything that works for plasma, would have stuff like this all the time, right? Straight line, straight line, straight line, straight line, straight line. Anyone run a plasma before? What happens at the end of a straight line? What does it do? So it's cutting, it's burning, burning, burning. It's coming to the end. What does it do? It slows down and stops, and then it moves. Then it changes direction, right? What happens right there at that spot? It burns it out. That spot gets a bigger cut because it slows down and stops there, and the plasma's still going, and then it changes direction. So what I used to always do, anytime there's a corner like this, I would add a little radius. So that way the laser would go, slow down a little bit, but then keep going. It would never stop. If there's a hard corner, it's going to stop. Even if it's just a little tiny bit. If there's a tangent, it just keeps going. So lasers, water jets, plasmas, all do the same thing. And so I would add little radius in there that they wouldn't see in the final thing. But it made it easier to make it. And it wouldn't have that big burnout there or anything. So that was just part of my process for designing it. Okay? So if you get to do something where you're going to be programming a plasma or laser or something, keep that in mind. Just little, like a 1/16 of an inch. Can't really tell what that is when on the finished product, especially if it's going to be bent up on a flange or something, or even like a 0.03, like a 30-second radius. That's super tiny, just enough that it's going to not dead stop.
And that would be the definition for the single limit.
And so that's kind of this. I would just throw that in everywhere, even if they didn't call that out, because it's not going to affect. Because sheet metal stuff, it's in the flange right here. No one's going to care about that. And actually, the sheet metal would go down. We'd do the bend relief right there. So I'd do that corner, that corner, that corner, and that curve. That one would be straight now. But I do all those corners, so it wouldn't stop and burn out as it did that little notch. Any question on this? All right. So then we have some sizes that we need to talk about. So the nominal size is the general size of that hole. So all of these, the nominal size is 1 inch, right? Because if you had to just talk about this hole, you'd say the 1 inch hole, right? They're all about an inch. basic size is the size that the tolerance is applied to. So what's the basic size right here?
What?
1. What's the basic size right there?
0.99.
0.999. What's the basic size right there?
There isn't.
There isn't one. Correct answer. Usually people look at that for like 5 minutes. We're like, I don't know. No, limits tolerances don't have a basic size. That's just giving you the tolerance, it's not putting the tolerance onto another number. So all of them have the same nominal size of 1 inch. The basic size is, there isn't one, just NA, 1 inch or 0.99. 9. Okay? The actual size is how big it's actually made. So when we actually drill this hole, and we measure it, what is that size? That's the actual size. Okay? And then the allowable minimum clearance is, now that we've got, maybe a screw's gonna go through here, how much space is there between the biggest size of the screw and the small size of this hole? So would this be a good hole if I was gonna use a 1 inch screw? 1 inch bolt going through it?
Yes, you can make it.
No, because that hole could be 998, right? 1 inch bolt is probably not going to be 998 or smaller. We'd want this to be bigger to allow clearance for that bolt. Okay? So in that case, we might have it where
You make it run.
we call it out here, and we call out plus plus.
Yeah, I was about to ask that.
And so I can say plus 5 thousandths and then plus 15 thousandths. So it's still a nominal size of 1 inch, a basic size of 1 inch, but the actual size isn't going to be 1 inch. There's no way the actual size can be 1 inch. The actual size has to be between 1.1005 and 0.1015. Okay, so the actual size in this case is not going to be the basic or nominal size. And so what kind of tolerance is this? I list 3 types. Unilateral, right? 2 different numbers. They just both have to be on the same side of it now. Okay? That's something I didn't learn about in school, but it happens all the time. Okay? Questions there? Yes, no? All right. All right. Here's the hard part. So what's baseline dimensions?
How long something
We just talked about it like half an hour ago.
How long something is?
No?
It's gonna start from 1 point all the way.
Yeah, all the measurements start from the same thing and go across, right? So here's this part. This dimension, I have an overall dimension here. I have a dimension from this side to here, the side to here, the side to here. And then this part right here, there's no dimension, right? So if I had this dimension, that'd be too many dimensions. And so, because
I know you can figure it out really easy, but
yeah, that's what we're going to talk about. So some people will put this dimension, and that's wrong. And we're going to talk about why it's wrong. Okay? So the drawing wouldn't have this A dimension, okay? That A dimension is not there. I just put it here so we can talk about A. So in my title block, it calls out a block tolerance of 2 decimal places to be plus or minus 0.03. How big can A be? How big is A? So let's just do, how big is A right now? Just not including tolerances. How big is it?
0.12.
Just 1.5 minus 1.38, 0.12, right? So that's how big it is, not if everything's made perfect. Things are not made perfect.
So it just gotta be whatever it would be.
So what's the size that this could be? What's the biggest that could be? 1.53. 2 decimal places, 0.03 tolerance. What's the smallest this could be? 1.47. What's the biggest this could be?
1.40. No,
4.1. What's the smallest that could be?
3.5.
3.5, right? If I did a little math there, so if I take the maximum size of this, subtract the small size of this, that gives me 0.18. Means that this A could be 0.18 big. If I take the small size of this and subtract the biggest size of this, that gives me the small size of the A could be, and that'd be 0.06.
Anywhere between both of those.
And so this size right here could be anywhere from 0.06 to 0.18. Because it's only, we're worrying about these two dimensions, right? Does this dimension have anything to do with the size of A? No, right? Does one have anything to do with A? No. So I'm just having to deal with these two. And so basically, once I have two dimensions, I get a tolerance stack of 2 times the tolerance. So now it's plus or minus 0.06, right? Because 12 plus 6 is 18. 12 minus 6 is 6. Does that make sense? What if I put A here? What if I actually put this dimension?
Your tolerance level would be like.
So if the drawing actually had this dimension on it, what's the tolerance on that? No. What's if this dimension was actually there where A is? What would that tolerance be? It'd be 0.12 plus or minus 0.03. So now which is right? Is it the 0.03 or is it the difference up here, which is 0.06? Right? That's why drawings won't have all the dimensions. So if they did, you wouldn't have any space for those tolerances to stack up. Nope. Try, but it's not always going to happen. You're going to get lazy and not brush out the chips, and it's going to be a chip stuck against your stop. You slide it over on the bandsaw. Now that piece is a little bit too short. Or you jam it in there, and because at an angle cut, it digs underneath your stop. Now your piece is a little too long. So this is why we don't put all the dimensions, because that would be different than what we did with the math. So that's called tolerance stacking, okay? So in baseline, all we have to worry about is those 2 dimensions here, or in that case. What if I cared about this part right here? What dimension is what I care about? What if I did care about this dimension there? Yes, now I care about these 2 dimensions, right? But still, it's only those 2. Do I care about this dimension? No. Do I care about this dimension? No. I still only care about those 2 dimensions, okay? So now, same part, but now is dimensioned using chain dimensioning. Still same size overall, same measurements, but now it's dimensioned with chain. Can you tell what's going to happen here? Now I have to add all 3 of them. So I have a tolerance here, a tolerance here, and a tolerance here. So basically I'm going to have the big size of this minus the small, the small, the small, and now this piece can be 0.24 big. So now, like instead of being an 1/8 of an inch, now it can be a 1/4 inch. But also, this is made small, and all 3 of these are made big. There's nothing left there. But so the sizes would work out, but would it be the same part? No, because it's missing a piece of the part. But based on the sizes, it'd meet the tolerances. So in that case, it'd be like, bad designer. They shouldn't have done it that way. Okay. But why? So we see that, right? What if we cared about this measurement right here? We actually care about that 3/4 inch measurement. Which would be better, chain or baseline? I think baseline. If I actually cared about this width being 0.725, which one is better? Really? I do this. What's my total tolerance there? How many dimensions are making up that number? Two, right? This dimension and that dimension have to go to work together to make that number, right? So if I'm using 2 dimensions, what do I have to do? I have to have twice the tolerance. So same thing here. I have 0.06 tolerance, right? So it means that if I dimension it this way, it'll be 75 plus or minus 0.06. I go here. Now what is this? What's the tolerance on this section? Plus or minus 0.03. So the things I care about are dimensioned continuous between those two things that I care about. Does it have to be either this way or this way?
No.
No, I could mix. So if I care about this and this, I could make,
Put those in none of those.
I could get rid of that dimension and add that one, right? Now it's this dimension, baseline to here, and now continuous from there to here, so I can make sure that this stays the same size, but also this one's not going to get the most, and then back to the baseline for here, so that I know that that's going to stay there, okay? So on drawings, you're not going to see all baseline or all chain. They're going to be mixed. But the point of this is that knowing that anytime you got dimensions added up, the tolerances are going to add together also, okay? Or if you have dimensions on either side, now you just have to take both tolerances into account, okay? So that's an important thing to realize, okay? One thing, that's one of those things that I didn't really get while I was in school. Didn't explain kind of how that all worked. So here I've got a little animation showing those. So you can see here in chain, the green line is the ideal distance, and the purple or the little pink is the size of the tolerance zone. And so in chain, as the part moves, the tolerance zone moves. This one moves a little bit, this one moves a lot. In baseline, the tolerance zone stays the same, stays still, and the part can just move within those. Okay? Does that make sense? Does that kind of make it click a little bit more? But also remember here, right now in the animation, these are going together, but they could move opposite too. Okay? Any questions?
So can we say the chain is broken up and the baseline is solid? As far as
No, chain the dimensions are end to end, and a baseline they're not connected.
okay.
But a baseline, our tolerance, the areas where they can be, stay still. And chain, they move based on that previous thing. Yep. All right. So now how do we use tolerances? So the most common way is when we're having things fit together somehow, right? If it's the outside of the part, we really don't care about the tolerance that much. That's where it might be the 2 decimal places. If just air sitting in it, we don't care. Maybe we can drop to 1 place, right? I mean, it's not going to fit into something. It's off. Who cares? So I did this earlier. I had this little smart switch that I got from a friend, and he didn't include a housing for it. And so I made a housing. Drew it up, and the main part of the switch fit through fine, but the first one I printed didn't fit together. because this part went in fine, but this right here had to go into a little slot there, and it didn't fit because of how the 3D printer made it a little too big. And so I didn't take into account the fit based on the 3D printer. I thought I had, and I didn't use the right number. So I had to reprint it with a better fit, so now it slides in there perfectly. Okay? So, but the outside here doesn't matter, right? The curve's not exactly perfect, but it doesn't matter because it's not hitting anything. The side out here doesn't matter how wide this is. If it's a little wider than I drew it, that's fine. Nothing's there. But where it interacts with other things, that's where it matters. Okay? So that's the fit. So these are called fits. And so there's three main types of fits. There's clearance fits, where things are always going to fit together. It's like here, I want that always to fit together, right? You have a hole that a bolt's going to go through. You want that hole to always be bigger than the bolt. We have things that we can have them where we want them always to interfere. So when you're pressing a bearing, you want the hole for the bearing to be a little bit smaller than the bearing. That way the bearing doesn't fall out, right? A little bit smaller. Other things, you're going to want it to be even smaller, so it's going to be even a tighter fit. That way you can push them together and they stay together forever without having to add glue or weld or anything like that. And there's some things that they can be either one. Okay? So those three kind of fit into different classes. So the first class is running and sliding. So when we're talking about this, sliding means moving across each other. Running means turning. It's like a shaft, like your crankshaft, that's running. Your car's running, right? But the crankshaft is turning. So that's a running fit. Sliding fit would be the piston sliding up and down. Okay? And so running and sliding fits allow space between the two parts for lubrication. So oil, grease, whatever. Okay? Does that make sense?
So something has to move across.
Yeah, so these fits allow for, based on the size of it, they allow some space to allow some lubrication fluid in there somehow. Okay? Locational fits are fits we use. So running and sliding fits are always clearance. We always want space between the side of the piston and the side of the cylinder. We don't want them to bind up, right? We use the rings in the piston to just make a seal so that lubrication doesn't get up into the head. But the actual piston itself is always going to be smaller than the cylinder. Same thing, the journals on the crankshaft are going to be a little bit smaller than the bearings that are in there, right? Because if it's not going to turn. We need a little space for some oil to get in there to help keep it going. Whatever. I don't know. I'm not a mechanic. My car doesn't have an engine. I don't care. Locational fits are ones where we're just using it to line stuff up. Things aren't going to be moving. When we're actually using the part, they're not going to be moving. They're going to be holding still, but we're going to use it to line stuff up good. So like this, it's a locational fit, right? I needed that to locate it in there, but I'm not going to be sliding this in and out while it's moving. So within location, we have three types of location fits. We have LC, so location clearance. So up here we had RC, running clearance. So here we have LC, location clearance. We have LT, location transition. And then we have LN, location, what's N? Anyone take physics in high school or physics here? No one took physics in high school? No? In physics, N means force. The unit of force is a Newton. So N represents force. So location, force fit is what it means. Okay? Whenever people that come up with this, these standards are what? They're engineers. They do a lot of physics. So location clearance, location transition, location force. So force fits, the hole is always going to be smaller than the shaft. So when we talk about this, we'll talk about holes and shafts. So it just makes it easy to kind of see in your head. So on here, even though it's just a slot, it's the hole dimension. The thing that's going into it is the shaft, okay, even though they're rectangular. That's just the way we talk about the fits. Just the thing that things are into are the holes. So if it's we got a part that's got a slot like that, that's the hole dimension. So the width of that, that's the hole dimension. The thing that's going to go into it, the width there, that's the shaft dimension, even if it's square. Okay. The height is different, but for the width of that, that's where the fit matters. Hole, shaft. So if you cut out a hole in a shaft in half, you'd see the same basic shape, right? Right. So we just use that terminology. So we just talk about one thing. You're not to say, okay, the hole or the slot or the right? We just say the holes in the slots or in the shafts. So location clearance, the hole is always bigger than the shaft. Location force, the hole is always smaller than the shaft. Location transition, it can be either one, depending on how it's made. So that means the tolerances overlap. And I'll show you this on the next, or like 2 slides. Okay. Then we have force fits. These are ones where we want the parts to stay together for good. They need to be able to transfer power from one part to the other without slipping. We don't want them to be able to come apart with vibration or anything. So, and they're going to be tight fits. So they're FN. So force. Okay. Questions? No. So these are the ANSI or ASME fits. Okay. Yep. Location. Yeah. So locational. So we're using that to line stuff up. And we're using it just to line stuff up and assemble to put together. Right, and sliding means it's moving. While it's working, it's going to be moving. So then we have ISO fits. So this is one area where you might see ISO fits called out on an ASME drawing. I like to do this. You go through and look at the drawings for the quizzes on that vise. Things are called out like this. This is an easier way to call out the fit. And like the way to read it is a little bit easier. So I like this better than calling out an ASME fit. Okay. And so what we have here is the first number is the basic size. Right? That's the size we're applying the tolerance to. And then we have a letter and a number. A capital letter means that tolerance is applying to the whole. A lowercase letter means that tolerance is applying to the shaft. So on a part where I'm seeing the hole, I could see just this. So 50 millimeter hole, H, or capital H, because it's applying to the hole, that's capital, and then a number. If I'm looking at the shaft, it'll call out 50, then a lowercase letter, and then a number. So hole or shaft, or it could have this on either one of them. And calling out both the hole and the shaft. So telling it the total fit between the two pieces. Okay? Either way is good. So a hole could have this or this, and the drawing of a shaft can have this or this. Okay? Both are right. So what does that mean? So it tells us that the F is the fundamental deviation. What does that mean? Right? So here's the chart that tells us what that means. So A through G are clearance fits. Means the hole is going to be bigger than the shaft. H means it's a location fit. It's going to be a tighter fit. So it tells us location fit, right? It gives us some examples. K through N are in transition fits. It could be either clearance or force fit, depending on how it's made. And then P through Z are all force fits. Okay? Does that make sense? Just know H is the dividing line. Why is H the dividing line? What starts with H? The hole. So the side of the hole is the H. And then the number is the grade. So if we look at this chart here, so if we look at this, so let's look at 16. So the grade basically tells you kind of what kind of process is going to make something that has this tolerance. So 16 can be done with sand casting. Is sand casting a precise thing? No, it's a rough finish, not exact. So the higher the number, the looser the tolerance. They're not going to make a sand casting adhere to a really tight tolerance. That's not going to happen. Because you've got how it's packed, you've got shrinkage, you've got all these things. That's not going to hold a really tight tolerance. As we come up, now we're going to do die casting. Die casts, like Hot Wheels cars, are a lot more precise than a sand cast. Then we get up into drilling at 11, milling at a 10, and then high quality turning and grinding up here at 6, and then fine things at the very bottom. Okay? So the lower the number, the more precise the tolerance has to be. So that means the less spread between those numbers. Right? So now we're down here, it's at, I don't know, plus or minus 0.1. And down here it's plus or minus 0.00001. Okay? Does that make sense? I'll just use those kind of examples. So let's kind of see what that means. So here's a little chart. So I'm going to tell you what this chart is. So if I take my hole, here's my hole, right? And then if I take my shaft, and the shaft is smaller than the hole, I slide the shaft down so they're touching on one side, right? Right, this chart is looking at right here. And so, like here, the shaft is smaller than the hole. The shaft is smaller than the hole. And the shaded area is how big the tolerance zone is. So what the sizes are. So it's here. They're both touching the same side. From measuring from here to here, and here. That's the difference in diameter that I can have for that shaft. Does that make sense? Kind of. And then this is the hole here, and the hole can be bigger. So the hole is here, the blue line, and then that's how much bigger the hole can get. And the length of this line depends on the number here. So you can see 11, bigger number, more tolerance than a 7. Okay? So that's that line. This line here is how much tolerance I have there. So from the smallest size the shaft can be to the biggest size that shaft can be is that, right? That line is how long this is. The space between the blue and the orange circles, that's this space. Now, does it make sense? Kind of, a little bit more? Basically, looking at this chart, we can see if we have an H11, C11 fit, it means we've got a big size tolerance on both pieces, on the hole and the shaft, and we have a big space between them. A D has less space between them. A 9 has less space, less size tolerance than an 11. A 7 has less than a 9, but a 7, F7, the same height as an H7. A 6 is smaller than that, but all the 6s are the same height, or about. Okay? But so H, they both line up right there. So a capital H and lowercase h both start at the same point. Capital letter goes up, lowercase goes down. So at this point right here, where they're both on H, it's called a line fit. Means it's going to be clearance, or they're going to be exactly the same size. They're going to be on the line. Once we get into here, these are our transition fits. So if the hole is made here, and the shaft is made here, what kind of a fit is that? Is it clearance or interference? It's clearance, because the hole's still bigger, right? If the hole's made down here, and the shaft is made up here, now what is it?
Interference.
Now it's interference. Okay? So depending on how they make the two parts, it could be either one. Okay, does that make sense? This chart making a little bit more sense now? And we've seen this makes a lot more sense to me than just looking at a table of numbers that they give you for answers. And I'm going to show you some other stuff that'll help you see this a little bit also.
So for the hole, it's always going to be H.
Yeah, it'll be H and then a number. And then the shaft will change. Or in most cases. Because usually you have the things that are making the holes are a set size, and shafts can be turned to whatever size you want. So it's easier to do that. So that in ISO, there's the hole-based system, which is what this is. There's also the shaft-based system that you can use. In that case, the shafts would all be H and the holes would get bigger. But that's not as common. But that would be like if you were buying a shaft, there was a standard part and it had a specified diameter, you weren't going to machine it yourself. And so your hole has to be bigger than that. Then you might use the shaft system. But in most cases, that'd be using the hole system. It works the same way, it's just now that's an H and this is now the letter. Now this is the G, F, D, C. Same thing, the lower the letter, closer to A, the more space you're gonna have between the two parts. Questions? Is that it? That was it. Hey, we made it. So that was the next 4 pages in the standard. So here on Canvas, there's the standard. So if you want to look at it, go for it. I encourage you to skim through it at least. There's a lot of good stuff in there. If you have questions about drawing, like you don't know what a drawing means, that's where the standard is good. You can open up the standard, turn until you find something that looks like what's on the drawing, and it'll tell you what that means. Down here for tolerances, we've got some stuff. So we click on this link. It's going to take us to the Wikipedia page, and it's going to show you kind of, so here's that same thing I was trying to explain. That chart that I had, the hole and the shaft are lined up on one side, And then here we have where they are. So this would be my H, and then kind of the size, this would be the gap between, and then the size of the tolerance for the shaft. And looks like some of the stuff is gone. I'm just going to open all these. So here, there's another website that kind of goes through and explains everything. So it kind of has a chart here that lists the different clearance fits. So from free running to close clearance, and then to locational clearances, and then the transition fits and the interference fits. And over here, we have the ISO fit. So like I said, the whole system, where the hole always is the H, and the shaft gets bigger, versus the shaft system where the shaft is the H and the hole gets bigger. So you can see here, it's a capital H, lowercase d, under the hole system. Under the shaft system, it's a capital D, lowercase h. Same letters, now they just get switched between the parts. And so there is a link between the ISO fits and the ANSI fits. And so this kind of explains hole weight versus the shaft system. And so it's got a few pages that kind of go through talking about different things. So this is a good one if you want to see more of what that is. So here it tells you more about the letters and then the numbers and everything. Oh, that was that same page. Another page that kind of, here you can see that picture that I tried to draw on the board a little bit easier. Now you can see the kind of the whole thing. And same thing, the charts and everything. So for some people, some of these charts make more sense than other ones. That's why I put them all there. So here's another one with the charts. And so this is the ANSI chart. Okay. And so if you need to look up, so the drawing might say the number and then H6 on it. Or it might say RC1, RC2. So it might have the actual tolerance listed, or they might just call it the fit. If they call it the fit, then you have to figure out what size to make it. Okay? So the way the chart works is at first you come down the side to figure out what size it is. So let's say I was going to do a 1/2 inch hole. So I'm going to come down there here until I get to the 1/2 inch. So 1/2 inch is between 0.4 and 0.71. So I'm in this row. And now it's based on what class of fit. So RC1, 2, 3, 4, 5, 6, 7, 8, 9. So there's 9 RCs. Then we get to the LCs, and then the LTs, and then LNs, and then the FNs. Okay. I guess you have to figure out that first. But so let's say I want to do a RC2 fit. Okay. So it's a 1/2 inch RC2. That's going to be that set of numbers. Okay. So while I'm talking about the hole, then I care about these ones, right? So for the hole, my tolerance is going to be that and that. So what's this note right here say? Values are shown in thousandths of an inch, right? So my hole size is 1/2 inch, right? My tolerance is going to be plus 0.0004 minus 0. That's 0.4 thousandths. So thousandths is there, 0.4 moves it one more place. So a RC2 fit for a 1/2 inch hole, it has that much space. Okay. The shaft that's going to go into that has that tolerance. Okay, see, negative, negative. Okay, should be 1/2 inch, negative, negative. Okay, so now that hole diameter, I've only got 4 10,000ths of an inch of tolerance on the diameter total. A lot more precise than else. So lower numbers have tighter tolerances. So an RC2 fit is a lot tighter of a clearance fit than an RC9 fit. Okay. If we look down to an RC9, or let's see, let's do a 6, that way I can put it in the same spot. Of course, it's not lined up. This was RC2, right? So this is going to be RC6, 0.5000 plus 0.0016 minus 0. A lot bigger of a tolerance, right? Okay, so that's how the table works. So if you're at work, you have to do something like this, you'd use the table, you look it up. Better thing to do though would be to bookmark this calculator, and I can say RC6 0.5, and it tells me right there 5016 to 5. And it also tells me that that is an H9 fit, which was the same as, oops. So RC6 H9 E8, H9 E8. So that H9 E8, that's the ISO fit. They line up with each other. Okay. This tells me the minimum maximum tolerance, the minimum maximum hole size, the tolerance, and then down here it tells me the minimum and maximum clearance between the two parts. Okay. So the RCs through the LCs are all, or through the Ls are all on the same page. If I want the force fits, I'd have to go here to look at those. And the standard ANSI B4.1 is a standard that covers limits or fits. Okay. So if you want to read more about that, try and find stuff on that. There's also a fit calculator from the same website. This website, Engineer's Edge, they have a lot of good calculators. I like to go to them for a lot of stuff. They also have the Tabular chart, right? So here I can tell it kind of which things, and so which, tell it what it is, tell it the diameter, and it gives me tolerance. I can also look at the preferred gauges. So for clearance fits, these are the pairs. Transition fits those, interference those. Okay. Questions on any of that? So you do have 2 quizzes to do, 7 and 8. You don't have to do them both today. I know I've been talking a long time. Work on quiz 7 or work on 8. Pick one, work on it. Get it done. Have a good weekend. Okay? Do the other one, like try it at least once tomorrow or Saturday. I know you're not going to do anything Sunday. And I'll get this video uploaded so you can see it.